Welcome back, everyone, to our exploration of functional analysis. In this episode, we delve into the world of spectral decomposition, focusing on the profound properties of self-adjoint compact operators. Whether you're a first-time viewer or a dedicated member of our mathematical community, your presence is the cornerstone of our quest for deeper understanding. If you are new here, consider this as an invitation, right? An open invitation to subscribe to our channel and become an integral part of our ever-growing community. So, one of the key highlights we'll be emphasizing in this lecture is the fundamental property that distinguishes self-adjoint compact operators, notably the existence of a Hilbert basis, right, comprising of eigenvectors. This unique characteristic enables us to simplify the operator's representation, right, paving the way thereby for a deeper understanding of its subtleties, right, and underlying structure. So, in this, throughout this lecture, right, we will assume that. So, what follows? What follows, we will assume that it doesn't look nice. We will assume that H is a Hilbert space. Right, and T is actually a linear bounded operator on H, right? Now, by identifying the dual of the Hilbert space H, right, with H itself, we may actually we may view the adjoint of the operator T, T star, as a bounded operator from H into itself. Okay, good. So, definition, by the way, the identification of H star with H is actually being done by the Rees representation theorem. So, definition. So, a bounded operator T is said to be self-adjoint if the adjoint of T equals T, right? So this means that the agree pointwise, right? So this means that the scalar product of Tu and V, right? As I said, we are doing the identification of the dual space with the space itself. So this is exactly the scalar product of U, TV, right? And this holds actually for every U and V in H, right? Okay, so let's have our very first proposition. So proposition 6.9 So let's see. Be a linear bounded operator, right? I mean, be a self-adjoint. Be a self-adjoint operator, right? So let me just highlight self-adjoint, right? Now set small m to be the infimum of the scalar product of tu and u, right, over the u in H for if norm of u equals 1. And capital M is actually the supremum, the scalar product of tu and u, right, over the u in H if norm of u equals 1. Then the spectrum of T, right, is actually contained into the interval M capital M, right? M is an element of the spectrum, and capital M is also an element of the spectrum of T. Moreover, we can even characterize the operator norm of T as being the maximum, the maximum between the absolute value of small m and the absolute value of capital M. Okay, so well, this is just a kind of just a recall. This is actually, this is being viewed at times as the largest eigenvalue, right, of the operator T, right, and small m as the smallest eigenvalue. Okay, so let's go into the proof of the proposition. So proof. So maybe I should drag it down a bit. Okay, so let's go into the proof. So let's show first. So let's prove first that the spectrum of T is actually contained into the interval M, M. So we proceed by contraposition. So by contraposition, right, let lambda be strictly greater than M, right? So we assume first that lambda is strictly greater than M. So what we will do is that we will prove that lambda is an element of the resolvent set of T. Okay, so we have that the scalar product of T of U over the norm of U, comma U over norm of U, right, by definition of M, right, is actually less or equal than capital M, right, for every U in H, right, of course U different from 0. So this means that scalar product of Tu, comma U, right, is always less or equal than M times the norm of U squared for every U in H, of course. Right, even if U equals to 0, this inequality holds. So, and therefore, you have that the scalar product of lambda u minus tu comma u, right, is actually greater or equal than lambda minus capital M times the norm of u squared, right? But this is actually this is even equal to alpha times norm of u squared, right? Of course, this holds for every u in H, right? With alpha equals to lambda minus m, right? Which is obviously greater than 0, right? So greater than 0 because we assume that lambda is actually strictly greater than m. So this means that the operator A defined on H cross H cross H into R, right, which maps U comma V to lambda U minus Tu comma V, scalar product of lambda U minus Tu comma V. So this operator is continuous, cohesive, and bilinear. Right? So A is a continuous, cohesive, and bilinear form on H. So applying the Lax-Milgram theorem, right? This was actually corollary 5.8, right? We saw that the Lax-Milgram was actually a corollary of the theorem of Stampaccia, right? If I remember, yes. So if you don't know what the Lax-Milgram theorem is, I strongly invite you to watch my video on the theorem of Stampaccia and Lax-Milgram. So if you apply the Lax-Milgram theorem, and just highlight those, we deduce that lambda, times identity, of course, minus t beta times, we usually write lambda minus t, right? So we deduce that lambda minus t is bijective, right? Right, and thus lambda is actually in the resolvent set of T. So this means that lambda is not in the spectrum of T. Good, so this is basically what we wanted to show, right? Similarly, any lambda strictly less than m, right, belongs to the resolvent set, the resolvent of T, right? And therefore, the complement of the interval m comma m is contained into the complement of the spectrum of T, right? So which means that spectrum of T is obviously a subset of m comma n, right? For this, for the case lambda strictly, oops, doesn't look nice. So for this case, it's enough for you to consider scalar product of Tu minus lambda u comma u, right? And this is actually greater or equal than m minus lambda times the norm of u squared, right? I mean, you just go back in the proof for the case lambda strictly greater than m, and then you just replace the bilinear form by tu minus lambda u. Okay, so now let's prove that not strict, good. Now let's prove that I mean that capital M is actually in the spectrum, right? So I mean we are just going to prove this, right? Because the proof that small m is in the spectrum, right? I mean is similar, right? It's similar. Okay, now the bilinear form A of u comma v, right? Defined by the scalar product of mu minus tu comma v, right? This scalar product, I mean, it's not really a scalar product, but we will see that it is actually. This bilinear form is symmetric, right? And satisfies I mean, is symmetric and positive definite. I mean, A of v comma v is greater or equal than 0 for every v in H, right? Hence, A defines a scalar product, right? And it satisfies the Cauchy-Schwarz inequality. This is the absolute value of A of u comma v, right? Is less or equal than A of u comma u to the power 1 over 2 times A of v comma v to the power 1 over 2. And this holds actually for every u and v in H. So this means, I mean, if you replace A of u comma v by its value, then you get that the absolute value of the product of mu minus tu comma v, right, is actually less or equal than scalar product of mu minus tu comma u to the power 1 over 2 times, right, I will write it down here by scalar product of mu minus tu. Oops, I think this should be with v, yes, comma v to the power 1 over 2. And this, of course, holds for every u and v in H. So it follows that, so from this relation, it follows that, we call it 7, right? We'll come back to it later. It follows that the norm of m of u minus tu, right, is actually less or equal than a constant c, right, times scalar product of mu comma t minus tu comma u to the power 1 over 2, right? And this, of course, holds for every u in H. Well, how do you see this? Observe that we should consider this quantity here. Observe that, put it here probably, yeah, there's some free spaces. Observe that this is actually less or equal than the norm of m minus t to the power 1 over 2, right, times the norm of v. I should put v to be u minus tu, right, which is still an element of H, then you get that the norm of mu minus tu is actually also equal than the constant C times mu minus tu times, the scalar product, the square root of the scalar product of mu minus tu and u. Okay, so now by definition of M, right? Now by definition of M, right? That is by characterization of the supremum. By characterization of the supremum, there exists, right, a sequence un, right, of element of H such that the norm of un equals 1 for every n, right, and the scalar product of T un and un, right, actually converges to n. Now from 7, right, from relation 7, right, probably I should recall what 7 was, right? From 7, that was actually the norm of mu minus tu, that's equal than C times scalar product of mu minus tu and u to the power 1 over 2, right? So from 7 we deduce that the norm of mun minus tun converges to 0, right? And thus M is in the spectrum of T, right? Since, this is because, if it is not, if M is rather in the resolvent of T, right, which means that M minus T minus 1 is a linear bounded operator, on H, then un could be written as the inverse of M minus T, right, of mun minus tun. And this we actually converge. It actually goes to 0, right? Because you can basically put the limit inside the inverse of M minus T, like, which is obviously a linear bounded operator, and then we know that the norm of mun minus tun actually goes to 0. But this is actually impossible, right? Which is impossible, right? As norm of un equals 1 for every n. So you can conclude that M is actually, is indeed an element of the spectrum. So this is the end of this short proof. And finally, we prove that the norm of T, right, is equal to neta, right, where neta is actually the max of the absolute value of M, of small m, and the absolute value of capital M, right? And this is just a way of saying that the max of absolute value of M and and this. Okay, so now what we do is that right, for every u and v in H, right, the scalar product of t u plus v, right, and u plus v, right, this is, I mean, if you expand this, then you get that this is equal to the scalar product of tu and u plus scalar product of tv and v plus 2 times scalar product of tu and v. And also you do the same thing now with u minus v, then you get pretty much the same result, right? Except that here you rather have minus t times the scalar product of tu and v. So these two relation holds. So let's say this is A and this is B. So from A and B we get that thus 4 times scalar product of tu and v, right? It's actually equal to the scalar product of t u plus v and u plus v minus scalar product of tu minus v and u minus v, right? I mean, this is, as I said, this is just, I mean, this equality actually follows from this is A minus B. Okay, so now this is actually less or equal than, I mean, by definition of capital M, then capital M times the norm of u plus v squared, right, minus m, small m times the norm of u minus v squared, right, and of course this holds for every u and v in H, and therefore we have that 4 times the absolute value of the scalar product of tu and v, right, is actually less or equal than neta, right? You can even you can upper bound this term here, right, by the max of this of the absolute value of these two terms here times the summation of these two. So let me just write it down so you don't get confused. So 4 times the absolute value of the scalar product of tu and v is actually less or equal than neta times the norm of u plus v squared plus the norm of u minus v squared. Now what we do is actually, we see that, I mean, the right hand side is just, if you apply the parallelogram identity, then you get that this is equal to 2 times, I mean, 2 neta times the norm of u squared plus the norm of v squared, right? As I said, this is the parallelogram identity. So replacing, because H is actually a vector space, replacing V by alpha V, right, with alpha positive yield to the fact that, I mean, 4 times the absolute value, I mean, you can even drop the absolute value if you want. 4 times the scalar product of tu and v is actually less or equal than 2 times neta, the norm of u squared divided by alpha plus alpha times the norm of v squared. I mean, it's just about replacing v by alpha v and then simplifying stuff, right? So nothing, there's no black magic. So next, what we do is that next we minimize I will just write RHS for right hand side. So we minimize the right hand side over alpha. That means we choose alpha to be, if you do the computation, then the right hand side is minimized for alpha equal the norm of u divided by the norm of v, right? Of course, v should be different from 0. And then we obtain that the absolute value of scalar product, right, is less or equal than eta times the norm of u times the norm of v, right? And of course, this holds for every u and v in H, so that the operator norm of t is less or equal than eta. And we call this relation star 1. Of course, this actually holds because norm of t is actually the smallest positive constant for which the absolute value of the scalar product of tu and v is actually less or equal than the norm of t times the norm of u times the norm of v. Right? So now on the other hand, it is clear that the absolute value of tu, v, right, is less or equal than the norm of t times the norm of u. So I should put u here times the norm of u squared, right? So that if you take the infimum, right, observe that this is actually less or equal, greater or equal than scalar product of tu, u. So if you take the infimum, you first get that the absolute value of m, right, is less or equal than the norm of t, right? And also that the absolute value of capital M is less or equal than the norm of t, the operator norm of t, of course. You should take the supremum. And thus, you have that eta is actually less or equal than the norm of t. And this is star 2. So star 1 plus star 2 actually is, it's equivalent to say that the operator norm of t is exactly eta. So this is the end of the proof. And I think I went one step further at some point. I jump a step somewhere here. Where was that? Okay, star 1 here. In order to get the conclusion of star 1, as I said, maybe I write it here. Norm of t is actually is the smallest by definition, right? This is the smallest positive constant such that the absolute value of tu, v is less or equal than norm of t times norm of u times norm of v. So for that reason, you get that norm of t is actually less or equal than eta. So we are done with this proof, and now let's even characterize, if I have a self-adjoint operator, right, and then if I also know how the spectrum of that self-adjoint operator looks like, then I can even infer on the operator itself. So corollary 6.10. So let T probably I write the shortcut be self-adjoint operator such that, let me just highlight self-adjoint, such that the spectrum of T is equal to the singleton 0. Then I can then we can conclude directly that T vanishes identically, right? That T is actually the zero operator, the zero of the linear bounded operator on H. So the proof is rather straightforward, right? It's only one line actually. So for the proof, well, as I said, the proof is trivial, right? If the spectrum of T is actually singleton 0, right, then M and M are both 0, right? So this means that T is okay. So now so let me check something. Let me just check something very quickly. Let me just go back up just to have a look at something. Yeah. So let me just be a bit more clear here. Why M and M? This is because this belongs to the spectrum of T, right? And this we showed. Okay, so our last statement is actually a fundamental result, right? It basically has said that every compact self-adjoint operator may be diagonalized, right, in some suitable basis. So this is, this will be theorem 6.11. Oops. Okay, so let H be, we need the space to be separable this time. So let H be a separable Hilbert space. And let T be self-adjoint compact operator. Then, so let me just highlight the key point of this theorem. We need the space, the Hilbert space, to be separable. We need a self-adjoint compact operator, definitely. Then there exists a Hilbert basis composed of eigenvectors of T. I just realized that I didn't mention T in the I think I mentioned T is in the assumption. Okay, cool. So if you have a separable Hilbert space and a self-adjoint compact operator T, then you can always find a Hilbert basis composed of eigenvectors of T. You can basically, diagonalize your self-adjoint compact operator. So let's go into the proof. So let T, right, be compact operator, right, on self-adjoint. So we may assume that T so we may assume that that T doesn't vanish identically, right? Otherwise the result is obvious, right? So we now we know by theorem, I think this was theorem 6.8, right? I invite you to watch my video on the spectrum of a compact operator, right, where I discuss this. So we know from theorem 6.8 that first point, the spectrum, the point spectrum of T, right, is never empty. Sorry, is never empty. And we also know that, the point spectrum of T is actually the set of eigenvalues of T, right, just for your recall. So we also know that the point spectrum of T minus 0 is countably finite, right? If it is actually, we also know that if it is infinite, then we can label every element of the, of the spectrum, right, in the sequence that converges to 0. So, so let lambda n, right, be the sequence of all distant non-zero eigenvalues of T. Now put set lambda 0 to be 0. Sorry. So set lambda 0 to be 0 and the space E0 to be the kernel of T and En to be, the eigenspace, right? This kernel of T minus lambda n times identity, right? This, of course, for every n greater or equal than 1, for every n, right? So now recall that the dimension of E0, right, could be infinite. It's actually between 0 and infinity, while the dimension of En is always finite, right? So this, this was actually failed to capture the shape I want. Good. So this was actually by the Fredholm alternative. Right, Fredholm alternative theorem. Again, I have a very special video on the Fredholm alternative theorem, so please have a look at that if you want. En is actually the space of eigenvectors, right, associated to the eigenvalues lambda n. Now we claim that, so our claim is that H is a Hilbert sum H is the Hilbert sum of the ENs, right? And moving from 0 to infinity. So this means okay, so to prove this, we have basically two things to prove, right? So the first is that you have to prove that the spaces ENs, right, and running from 0 to infinity, right, are mutually orthogonal. So this is what you have to show first. So indeed, if you have U in, say, EM, right, and V in EN, right, with, of course, n different from M, sorry, with n different from M, then I mean, you can write TU to be lambda M U, right, and TV, sorry, to be lambda NV, right? This is because, I mean, this is just the definition of U being in EM and V being in EN. So that scalar product of TU and V, right, is equal to lambda M scalar product of U and V, right? Which is again, right, I mean, you use now, I mean, for the first equality, I use the definition of TU as being lambda MU, but I could also use the second definition, I mean, or the self-adjoint property first of T, right, and then, but this is again scalar product of TU comma V, because T is a self-adjoint operator, but this now is actually equal to lambda N of the scalar product of U and V. So this means, I mean, by equating both sides, I mean, they are already equated, so this means that lambda M minus lambda N times the scalar product of U and V equals to 0, right? But the lambda N's are all distant, so this means scalar product of U and V must be 0, right? Since, let me just write, since the lambda N's are all distant. So our spaces ENs are mutually orthogonal. So the last thing to prove, right, in order to show that H is a Hilbert sum of the ENs, so let F be the vector space spanned by the ENs, right? Spanned by the spaces En. So we shall prove, so let me just write it once again. So we shall prove that we shall prove that the closure of F is actually, I mean, that F is actually dense in H, right? So for this we use something very usual or common in functional analysis. I mean, if you want to prove that a closed set is actually dense in a Hilbert space, what you typically do is that you prove that the orthogonal of the set is actually the singleton 0. So for this we will prove that, let me write it here. So for this we will prove that the orthogonal of F is the singleton 0. So this is what we we aim to prove, right? So clearly, TF, right, is actually contained into F, right? And it follows that you can take it, right? It's actually very easy. So it follows that T of F orthogonal is also contained into F orthogonal. Well, this is a bit tricky, but also easy. Indeed, let's prove this inclusion. Indeed, given U in the orthogonal of F, right, you have, by definition, that Tu comma V, right, is actually, which is equal to U comma Tv, is equal to 0, right? And this, of course, holds for every V in F. So that Tu is an element of F orthogonal. So T of F orthogonal is actually contained into F orthogonal. Now let's say T0, let's set T0 to be T restricted to the orthogonal of F. Right? T0 is obviously a compact operator on F orthogonal, right? And T0 is also self-adjoint. Now our claim is that the spectrum of T0 is actually singleton 0. So our claim is that the spectrum of T0 is the singleton T0. Now for the proof, suppose not, right? So assume that there exists, right, that we can find a lambda different from 0, right? Lambda in the spectrum of T, 0, since we know that the spectrum of T0, so since the spectrum of T0 minus 0 is actually equal to the point spectrum of T0 minus 0. I mean, this we prove in, I think, on our lecture on the spectrum of a compact operator. So please check it out. I'll put the link to the video. So since this relation holds, it follows that lambda is also an element of the spectrum of the point spectrum of T0. Right? So this means that there exists, I mean, if lambda is an element of the spectrum of T0, then I can find U in the orthogonal of F, right? U different from 0, such that T0 of U is equal to lambda U. So basically this U is actually the eigenvector associated to the eigenvalue lambda. So therefore, lambda is one of the eigenvalues of T, right? It's one of, because T0 is actually just the restriction of T to the orthogonal of F. So therefore lambda is one of the eigenvalues of T, right? Say lambda is equal to lambda n, right? With n greater or equal than 1. So thus, in this case, you have that U is an element of the eigenspace En, right? Which is a subspace of F. Right? I mean, En is actually the kernel of T minus lambda n. Now, since U is an element of the orthogonal of F, and at the same time an element of F, right? We deduce that U is the zero element, right? Which is a contradiction. I mean, which contradict the fact that U is an eigenvector. So the spectrum of T0 is indeed the singleton zero. Now, applying corollary 6.10, we can conclude that T0 is actually the zero operator. So applying corollary 6.10, we deduce that T0, right, is actually the zero operator. So this means that T vanishes on F orthogonal. So it follows that the orthogonal of F, right, is contained to the kernel of T. Right now, on the other hand, the kernel of T, right, is contained to F, right, because F is actually the vector space spanned by the unions. So the kernel of T is obviously an element of, I mean, it's actually contained to F. So it follows that F orthogonal is contained to F, right? So I mean, this basically comes from this here. So these two things are what implies the fact that F orthogonal is contained to F. So this implies that F orthogonal is the singleton zero. And so F is dense in H, right? So therefore, because ENs, I mean the spaces ENs are mutually orthogonal, and that the vector space spanned by those ENs is dense in H, you can conclude that H is indeed a Hilbert sum of Hilbert sum of the ENs, right? N running from 0, 1 up to infinity. So finally, we chose, remember we want to construct the basis. So finally we chose in each subspace, sorry. So finally we choose in each subspace En right, n running from 0 up to infinity, a Hilbert basis, right? to tell you how this is possible. So in fact, the existence of the existence of such a basis, right, for the space E0 follows from theorem 5.11, right? That theorem actually states that, I put it in another color, that every separable Hilbert space has an orthonormal basis, right? Again, this was already discussed in one of my lectures on Hilbert sums and Hilbert bases, so please check it out. It was very instructive and very nice actually. So every separable Hilbert space has an orthonormal basis, right? And we saw that, you saw in the proof that the construction of such a basis follows the Gram-Schmidt orthogonalization process. Now, on the other hand, for the other spaces En, right, n greater or equal than 1, the existence of a basis is obvious, right, because it is finite dimensional. They are all finite dimensional. This is obvious since they are finite dimensional. So now, the union of these bases, right? The union of these bases is, it's clearly a Hilbert. It's clearly a Hilbert basis for H, right? Composed of eigenvectors. Composed of eigenvectors of T, right? Well, I said clearly because let me just cycle. It's actually difficult to get the shape you really want, but well, good. So clearly because because H is actually the Hilbert sum of the En side. Okay, so finally let's have a remark. So well, let me just first close this proof. Now we can take a remark, the final one. So remark, let T be a compact self-adjoint operator. So let T be a compact self-adjoint operator. Oops. From, this is another sentence, right? So if you have a self-adjoint compact operator, then from the preceding theorem or the preceding analysis, so from the preceding analysis, right, we may write any element u, right, as the summation of the un, right, n going from 0 to infinity, right, because I mean H is a Hilbert sum of the n, right, with un being element of the space en. Then for this we get that, we get that tu, right, in the image of u, right, via t is exactly the summation of lambda n un, and running from 0 to infinity. And this is because lambda n is an eigenvalue. Now, given an integer k, greater or equal than 1, right, set, let me use this color now. So set tk of u, right, to be the summation of lambda n un, right, n running from 1 to k, right. Clearly, you can see that tk is a finite rank operator, right, and therefore compact operator. Hence compact, right? Let me just write it here, hence compact. And you also have that, this you can check, right? That the norm of tk minus t, which is actually the supremum of the absolute value of the lambda, right, over n greater or equal than k plus 1, that this actually goes to 0, right? Of course, as k goes to plus infinity, right? Recall that, in Hilbert space, every compact operator, not necessarily self-adjoint, is actually the limit of the sequence of finite rank operators. Well, how can you see that this actually goes to 0? So maybe I write it for you. So this is, observe that this here is exactly the supremum of the norm of the summation of the lambda n un, right, over n running from k plus 1 to infinity, norm of u less or equal than 1. And this is actually less or equal than the supremum, right, over norm of u less or equal than 1 of the supremum of the absolute value of lambda n over n greater or equal than k plus 1, right, times, I can even bound this by the norm, of this series of the norm of the sum of the un and running from 0 to infinity. But this is actually what the norm of u, right? So this is even, if you switch the supremum, right, you get that this is actually less or equal than the supremum of the absolute value of the lambda n over n greater or equal than k plus 1. Of course, this actually goes to 0 as k goes to plus infinity. So this is actually the end of this lecture. So I hope you enjoyed it. Thank you for joining, and we see again each other in the next video.